because the level of the silt deposition, the amount of silt deposition is different in case of alluvial soil and in non-alluvial soil. Okay, so the first basic term was alluvial soil, and the second term is non-alluvial soil. Generally, describe soil, and we differentiate soil or classify soil in two types. First one is residual soil and second one is transported soil. But the main origin of the soil is, it is formed by weathering action of the rock. Weathering action of the rock, what does it mean? It means that the rock is being disintegrated, or rock is being acted upon certain agents that are physical agents or chemical agents. So first one, to your soil, alluvial soil, was a transported soil. Okay, now the second type of soil, non-alluvial soil, which is other than alluvial soil, which all the other soils would be classified into non-alluvial soil, which is formed by disintegration of rock. Okay, this soil is not that much fertile in comparison to alluvial soil. Okay, so from the designing of irrigation canal, from that point of view, we would be classifying soils into either you are constructing an irrigation canal on alluvial soil, or you are constructing a canal on non-alluvial soil. Okay, so now the third definition is your silt factor. Okay, now while designing a irrigation canal on a alluvial soil, we know that on the alluvial soil we would be having silt deposition at the canal bed. Okay, so when we would be considering that silt deposition, we would be designing canal on that, considering that silt deposition in point of importance. Okay, so during the investigation, one scientist known as Gerald Lacey, he considered certain experimental investigations and find out that this silt deposition creates a good impact when we would be designing that irrigation. Okay, so this silt factor would be affecting the flow of water through the canal, and it would also affect the velocity of the flow, and in connection to the velocity of flow, it would also impact the discharge of the canal, and on that basis we would be designing the canal section. So this silt deposition should be taken into action, or should be taken into consideration while designing an irrigation canal. Okay, so the silt factor is defined as F is 1.76 under root mr. And what does mr indicates? Mr indicates the size of the silt particles that are being carried in the suspension of the water. Okay, so the F is 1.76 under root mr. Okay, now this silt factor would be, since we in last formula we learnt about that the silt factor is dependent upon the size of the particle. Okay, so the when we will consider very fine silt, the size of the very fine silt is 0.05 and the silt factor is 0.40. Like that, in fine silt 0.12, 0.60, medium silt 0.23, 0.85, coarse silt 0.32, 1.00. Okay, so the silt factor depends upon the size of the particles. Next we have coefficient of rugosity, that is also indicated as capital N. So this coefficient of rugosity, it affects the velocity of the flow. Okay, and it is also taken into action while calculating the mean velocity of flow. So R.G. Kennedy, we would be frequently taking names of the uh, two names of the scientists. One is R.G. Kennedy and other one is Gerald Lacey. Okay, so this coefficient of rugosity, it affects the velocity of the flow. And what does the coefficient of rugosity means? What is the roughness of your canal bed that would be affecting the velocity of the flow? Since we have to consider the roughness of the canal bed, and we have to, how we have considered silt factor, we are calculating the silt factor on the basis of the size of particle. So how we have calculated the silt factor? We have calculated the silt factor on the basis of the size of silt particle deposit. Like that only, how would we would be calculating the coefficient of rugosity? We would be calculating the coefficient of rugosity dependent upon the material that is used in the canal bed. Okay, your value of coefficient of rugosity is always dependent upon the type of bed material that is being used in the canal. Okay, the value of n would be 0.02225 in the case of unlined canal. Okay, earth means your canal is not lined. So in case of unlined canal, you would always be having the value of 0.0225. In some questions in university, if you are not given the value of rugosity, means value of n, so you can assume, as it is written in the examination, that assume all the given data, you can assume it as 0.0225. Okay, when the material is masonry, 0.02, and when it is concrete, 0.013 to 0.018. So the first factor was silt factor and other one is of coefficient of rugosity. Okay, should we move on further? Okay, next important factor, that is mean velocity. The mean velocity is defined as the surface velocity that from which with speed your water is flowing in a canal. Okay, so the mean, it is dependent upon the depth of water in the canal. We usually take as that the at the most top your velocity would be maximum and it would be decreasing as you move on to the bottom. Okay, so which velocity you would consider in designing the canal? Okay, that is a big question. Which at which depth you would be calculating? You can take at the top or you can take at the bottom. At the top you would be having the maximum velocity. Okay, and at the bottom you would be having the minimum velocity. If you design for minimum velocity, the canal section would be insufficient, and if you would design for the highest velocity, the canal section would be not be economical, it would be uneconomical. The cost of the canal would be increasing. So we have to calculate what is the mean velocity. So the mean velocity is always obtained at 0.6 d depth from the top. Okay, from the top of the FSL you would go down to 0.6 d and then you would get the velocity